Dear students, today in this particular lecture, we are going to discuss about probability distributions. When you want to learn probability distribution, you have to learn some concepts. So the concepts which we are going to discuss here are random variable, binomial distribution, Gaussian distribution, and Poisson distribution. One of the fundamental things in probability distribution is the concept of random variable. First of all, let us learn the concept of random variable. What is random variable then? The real number which is associated with the outcome of a random experiment is called a random variable. In some cases, the outcome is a number. For example, when you throw a die, but in some other experiments, for example, like tossing of a coin, the outcomes are qualitative. In this case also, the outcomes can be expressed in quantitative form. So this is the definition of random variable. You can easily see that whenever you perform a random experiment, the result which is associated with the outcome of the random experiment, that result is known as random variable. And there are two distinct random experiments they are telling you. One is the cases where the outcome is directly a number. In that case, the outcome itself is the random variable. But in some cases, the outcomes are qualitative, which you can convert into random variable, that is in numerical form also. To illustrate, suppose you throw a die. When you throw a die, the result of the experiment that it comes out with 1, 2, 3, 4, 5, and 6. Any one of this will be the possible outcome while you throw a die. So 1 is a random variable, 2, 3, 4, 5, 6. All are random variables in this particular experiment, random experiment. Now, for the qualitative type, let us go to the example of toss of a coin. When you toss a coin, it throws up either tails or heads. That is, we can put a symbol capital H for head and capital T for tail. In another way, I can write 1 for head and 0 for tail. So these 0 and 1 are numerical figures. So by designating 1 for head and 0 for tail, what we have done is that we have converted the qualitative results into quantitative ones. As I am discussing random variable, let me introduce you to two distinct type of random variables which in practice you are going to obtain even if they are numerical in character. One is your discrete type. In discrete type, you see this example of throwing of a die. You have 1, 2, 3, 4, 5, and 6. Here, between 1 and 2, you don't have any other value. That is, the result jumps from 1, next 2, next 3. So there is a jump, there is a discontinuity. So such kind of random variables are known as discrete random variables. What are the examples of continuous random variables then? The other type which I am telling is continuous random variable. Let us go to the experiment of measuring lifetimes of electric bulbs produced by a company. So here you can easily realize that lifetime can be anything. It can be 100 hour, it may be 100.2 hour, 100.25 hour, it may be 0 hour, it may be 0.1 hour, any value, any continuous value is possible between 0 to the expected lifetime. For example, if the company manufactures light bulbs with maximum value of life expectancy to be 4,000 hours, then you can get any value between 0 to 4,000, any fractional value also. So this experiment and the variable associated with this lifetime of electric bulb is an example of continuous random variables. If the random variables are discrete, then the probability distributions are different. If they are continuous, then you have different probability distributions. Before going to probability distributions, let me introduce you to the symbol of random variable. Random variable is denoted by symbol capital X, and the values chosen by the random variable or values that the random variable takes is generally denoted by small x. So the example of this tossing of a coin, then the capital X will be the random variable and 0 and 1 will be your small letter x. Now let us concentrate on probability distributions. While dealing with random variables and their probabilities, it is often found that there exists functional relationship between the values taken by the random variable and the corresponding probability. Therefore, we can express relation between random variables and their probabilities with the help of mathematical functions. These functions are called probability distributions. So what are probability distributions? Depending upon the nature of random variable, probability distributions can be either discrete or continuous. So this is your definition, but I will explain the definition with examples. Again, as I told you, there are two types of random variables in numerical way. One is discrete and one is continuous. So discrete systems, discrete values will have discrete probability distributions, and for continuous case you will have continuous probability distributions. In simple language, there is a function, and this function corresponds to the probabilities taken by a random variable. That functional relationship is simply your probability distribution. To illustrate, let us go down and show you this. Suppose capital X be a random variable and values taken by it are x1, x2, x3, etc. Then let f of xk be your function which corresponds to the probability of the variable xk. Probability of the variable xk. Then the corresponding probability is p of x equals to xk. Here f of xk represents the probability function and p represents the corresponding probability. So f of xk is also known as probability mass function if your xk is discrete. that is x1, x2, x3, like that. Discrete numbers are there as random variables, then f of xk, the function which corresponds to the probability, is known as probability mass function, and this p we call it the corresponding probability. You will see that the probability mass function and the probability value is same in case of these discrete probability distributions. In general, when you see, you will find that I can write probability of capital X equal to small x equal to small fx. What are the probabilities that this probability mass function f of x satisfies? F of x must be greater than equal to 0, and sum over f of x for all the values should be equal to 1, as total probability is 1. Let us illustrate this with a simple example. Again, we will take the example of throwing of a die. When you throw a die, then the output, that is the results, are small x equal to 1, 2, 3, 4, 5, 6. Any one of these values are possible. Can you tell what is the probability of getting 1? The probability is 1 by 6, because total cases is 6 and favorable case is 1. What is the probability of 2? That is also 1 by 6. Probability of each number is 1 by 6 here. Hence, I can write probability of capital X equal to 1 by 6 equal to fx. And when I sum over, then I will get sum over 1 by 6 times, and the result is 1. Here, your f of x equal to 1 by 6 is your probability mass function. What are the situations you get discrete probability distributions? One is binomial distribution, which models binary data such as coin tosses. One is Poisson distribution, where the examples are like count of library book checkouts per hour. So this will illustrate later on as we move on. There is an example which we'll skip for the time being. Let us now go to continuous probability distributions. As I already explained, continuous probability distributions will be for the random variables which are continuous in nature. For a continuous random variable, you have this f of x. This f of x is known as probability density function. This is not PDF, which we portable document format we keep on telling. This is probability density function. So probability density function integrated from minus infinity to plus infinity gives the value of the random variable capital X less than equal to x. That is, and the condition is their random variable lies between minus infinity and plus infinity. Okay, and here your fx, that is the probability density function, has the property fx is greater than equal to 0. Here integral of this probability density function is over the full range, that is minus infinity to plus infinity, is 1, since total probability is 1. I would like to show you or to point you out here an important thing, that here you cannot get probability for a point for a value, specific value capital X equals to x. You see that it is defined as probability of capital X less than equal to x integrated over minus infinity to x. In continuous probability distributions, it is meaningless to find probability for a particular value. This you will understand by the following example. Suppose you have done a random experiment of measurement of height of persons. If I tell you that what is the possibility of a person having having height 68 inches, that is exactly 68.000 inches, it will be 0. But in this case you can find the data or the probability between 67 and 68.5 inches. You can find that the probability that a person's height is between 67 and 68.5 inches. That you can easily find out, but you will not be able to get the value of probability for a particular exact value. Same thing applies to the example of your life expectancy of the light bulbs. You cannot get the probability that the bulb goes exactly 100 hours. Not possible. Then, how will you find probability for continuous random variables? You will do this one, that is probability x less than equal to x. Option 1. Option 2 is also there. Option 2 will be able to give you probability between a range by integrating the probability density function. Suppose you want to find probability between a and v values of the random variable, then you just integrate between a to b of x dx, and you will get the probability in between that range. What is the example of continuous probability distribution? Your very important example is Gaussian distribution. This height of persons selected from a large group of adult males, it will follow Gaussian distribution. One can show it. Anyways, we'll deal with Gaussian distribution a little later. Let us now move to binomial distribution. You might wonder why in this lecture we are discussing binomial distribution, why Poisson distribution. The very fact remains in that Guwahati University question paper, you will get problems coming from binomial distribution, you get problems coming from Poisson distribution, and many things. Even problems are coming from mean deviation. All these things are not properly included in your syllabus. Your syllabus says to learn Gaussian distribution and mean and variance of Gaussian distribution, to be more precise. But they are asking questions from binomial distribution. So let us learn binomial distribution. What is binomial distribution? If you consider a random experiment with only two outcomes, either success or failure, then in that situation we apply binomial distribution. Suppose you are performing capital N sets of n number of trials. Small n is the number of trials, and frequency of m successes are given by probability of capital X equals to small m equals to capital N small n cm q to the power n minus m p to the power m. 0 less than equal to p less than equal to 1, q is 1 minus p. First of all, what is p and q in binomial distribution? P is probability of success of the random experiment, q is your failure. And what is capital N? Capital N is the set of trials. In each set you are having n events. If you make only one set, then this n will be 1. Then probability expression will be NCM q to the power n minus m p to the power m simply. Why it is called binomial distribution? Because it has either success or failure. The experiments are of that category in binomial distribution. Also, if you look carefully, then you will see that ncx q to the power n minus x p to the power x, it is like binomial coefficient in binomial expansion of your algebra. So binomial distribution is following that category, that type. What are the examples of binomial distribution? Tossing of a coin, even throwing a die. Throwing a die, output either comes or it does not come. So we'll handle problems later on. Now comes your mean and variance. What is mean? If you go to simple statistics, then mean x bar for a set of data is 1 by n into sum over all these data, x1 plus x2 plus x3 up to xn. 1 by n sum over xj, j goes from 1 to n, and standard deviation square, which is also known as variance, sigma square, is 1 by n minus 1. N is the total data, x1 minus x bar, that is mean square, plus it continues up to xn minus x bar square. So this is your variance for a set of data. Now, how can you write mean and variance for probability distributions? If you have a discrete distribution, then mean is denoted by symbol mu rather than x bar. It is sum over j xj into f of xj. Xj is your random variable, f of xj is its corresponding probability. For a continuous distribution, the summation is replaced by integration over the entire range of the random variable. So your mu is equal to minus infinity to plus infinity x fx dx. Likewise, your variance, that is sigma square, standard deviation square, is sum over j xi minus mu square into f of xj, discrete type, minus infinity to plus infinity x minus mu square f of x dx for continuous distribution. So these are mean and variance expressions for probability distributions. Whether we will calculate? No, we are not going to calculate the mean and variance of binomial distribution, Poisson distribution, etc., because they are not asking questions that will lead to a massive exercise of time consuming. So we'll avoid that. Let me tell you what will be the expression for binomial distribution. The mean expression is np, small n, into e, and variance is npq. So this is all about binomial distribution. Let us move on to Poisson distribution. What is Poisson distribution? I repeat that its pronunciation is not Poisson, it's rather Poisson. Poisson distribution was discovered by Simon Denis Poisson, and it was published in 1837. If you have a random variable capital X, discrete type, then probability of capital X equals to small x equal to e to the power minus lambda, lambda to the power x by factorial x, x 0, 1, 2 up to infinity, and lambda is a positive number, where lambda is the parameter of Poisson distribution. Here your lambda value is np, n is the number of trials, p is the probability of success, and interestingly this lambda equals to np equal to sigma square. Poisson distribution is very interesting that here mean and variance are equal. Other distributions you won't have equal value of mean and variance. So only this lambda, which is equal to np, it defines your Poisson distribution. You don't need other values. It is very simple in that case. Now the question is, in which condition you are going to apply Poisson distribution. So Poisson distribution can be derived as limiting form of binomial distribution. In Poisson distribution, small n, number of trials, is very large, and np equals to lambda is a finite quantity. For a binomial distribution, these two conditions lead to Poisson distribution. Poisson distribution is a discrete distribution where the random variable takes the values 0, 1, 2 up to infinity, and the Poisson distribution has only one parameter. That parameter is your lambda, and I already explained that mean and variance are equal. Other things are not much relevant from our perspective. What are the examples of Poisson distribution? Number of cars passing through a certain point per minute during a busy hour of the day. One of the very important aspect of Poisson distribution is that probability in each success is very low. For example, number of cars passing through a certain point per minute during a busy hour of the day is very low. Number of suicides reported per week in a particular time is also very low. So those are the conditions, one of the conditions of Poisson distributions. Number of printing mistakes per page of a standard book also follows Poisson distribution. Next, let us go to Gaussian distribution. What is Gaussian distribution? Remember, Gaussian distribution is having a continuous frequency distribution, a continuous random variable related distribution. Here, a continuous random variable capital X is said to follow Gaussian distribution if its probability density function, I repeat, here it is density function, it is given by y equals to 1 by sigma root 2 pi e to the power minus x minus mu square by 2 sigma square. Sigma is your standard deviation, mu is mean of this distribution. You have the condition minus infinity less than x less than plus infinity. X lies between that, mu also lies between the same range, and your standard deviation is a positive quantity. How can you write the corresponding distribution function? This distribution function is written by using the concept of probability distribution function for continuous distribution, integration f of x dx. Here, probability of capital X less than x is 1 by sigma root 2 pi minus infinity to x e to the power x minus mu square by 2 sigma square dx. And the probability expression for an interval can be written as probability of a less than x less than b is equal to 1 by sigma root 2 pi integration between a to b e to the power minus x minus mu square by 2 sigma square dx. Again, I would like to tell you that being a continuous distribution function, you cannot get probability over a straight value, that is probability of capital X equal to X. Some particular value is not possible. I have already given two examples in the lecture, that of height distribution and the life expectancy of bulbs. Both these actually follow Gaussian distribution. Now, what you do is that you substitute z equals to x minus mu y sigma. If you substitute z equals to x minus mu y sigma, then an interesting result follows. Your y, that is 1 by sigma root 2 pi e to the power minus x minus mu whole square by 2 sigma square, this now goes to a new function in terms of z, 1 by root over 2 pi e to the power minus z square by 2. You can easily see by substitution. And now your mu becomes 0 and sigma equals to 1. That is, if you substitute the variable z equals to x minus mu by sigma in the expression for probability distribution function of Gaussian distribution, the system goes into the variable z, and interestingly it goes to a new distribution whose mu equals to 0 and standard deviation is 1. Then Z is known as standard normal variate and its corresponding distribution is known as normal distribution. In your examination, question is asked, what is the difference between Gaussian distribution and normal distribution? You can say that normal distribution is a special form of Gaussian distribution whose mu is 0 and standard deviation is 1. Mean 0, standard deviation 1. Let us show you the graphs. What kind of graphs you are going to get for Gaussian distributions. Gaussian distributions are widely studied because many of the probability distributions in our day-to-day life, even the biological and economics cases are of normal or Gaussian distribution type. Here the plot will be a bell-shaped symmetric curve which is foldable or which is symmetric about x equal to mu minus infinity to plus infinity. So this graph, which now my mouse is pointing, is the graph for y equals to this sigma root 2 pi, this one. Let us see how much is the data or probability occupied between different intervals in this Gaussian distribution curve, the next curve right now. You will see that between the mean and mean plus sigma, mean minus sigma, you have 64% data, 34 plus 34. When you go to mu plus 2 sigma and mu minus 2 sigma, you will get about 34 plus 40, that is 48 and 48. 96% data will be in between mu plus 2 sigma and mu minus 2 sigma. Likewise, you can carry on. One more thing for these curves is that the curve being exponential, it will never touch the x-axis. That is, both sides, it will continue to run indefinitely. Although in this figure it looks like that it is touching the axis. The curve is asymptotic. It does not touch. Let us see the plot of f of z. So this is the plot of f of z, that is the normal distribution plotted over versus the values of z. 0. As expected, you have the mean instead of mu here, the value is 0. And here you have 0 0.1, 0 0.2, 0 0.3, 0 0.4, etc. And the value, you will see that 68.27 percent data lies between -1 and +1. That is mu plus sigma. This is mu plus 2 sigma. 95.45. Between mu plus 3 sigma, it is 99.73%. So there these probabilities written. What are the properties? We have already told it's a mathematical abstraction, but in practice, many distributions are of this form in nature. The probability distribution is completely determined by two parameters, mu and sigma. That also we have shown you. The mean, median and mode occur at same point. This is very interesting. Mean, median and mode of Gaussian distribution occurs at x equal to mu only. Linear combination of independent normal variates, that is, you have two z values, then their linear combination is also a normal variate. Now, what is the utility of this normal variate? Why do you transfer the Gaussian distribution to normal distribution? What it does to us? It helps us to calculate probability. How? Suppose you want to find the probability in a range. Again, I repeat that it is not possible to find probability for a particular value. We cannot calculate probability at a point. But probability between C and D. Suppose you have to find the probability between C and D of this x. That is your random variable x. Then you have to find the area under the normal curve between the lines C and D. Okay, I will draw and show you. Suppose this is your normal distribution. These are the two values. This is your C and this is your D. Okay, and here this is the mean line. You have to find the area between this. This is your x1, not for that z1. That is, this is your y equals to fx graph, this normal distribution, Gaussian distribution graph. Finding that one is not easy, it is difficult. So what we do is that we transform by taking the value in z. That is, you convert this distribution, this Gaussian distribution, into a normal distribution, and C is replaced by, you will see that C dash, which is C minus mu by sigma, and D is replaced by D dash, D minus mu by sigma, and now instead of x it goes to z by substitution, and these are C dash and D dash. You will convert the Gaussian distribution into normal distribution and you find the area here between C dash and D dash. It is much easier because you have standard tables which will give you the data, that is the standard normal variate, and its values are available in standard tables. Let me show you. Suppose you want to find the area here in this shaded diagram. Minus infinity to 0, the area will be 0.5, and area between 0 to a, that will be given from the area under normal curve standard table. What is that standard table? This is your standard table. You can get 0.0, and if you go here, then the value is 0.01, its value is 0.0040. Area for your value of that a, this a, to be 0.01. Suppose I want to find 1.12, so I will go to 1.1 and 0.02. 1.1, 0.02, the corresponding value is 0.3686. So if your standard normal variate has that 1.2, that is a is 1.2, you can find its area. More of finding this area I will show you in the corresponding next lecture, where we will discuss numerical problems. This is what we had today in your discussion. To re-summarize what we learned about random variable, we learned about binomial distribution, we learned about Gaussian distribution, we learned about Poisson distribution, and in addition to these, we learned about mean and variance of probability distributions. Next lecture will take problems of all these parts. Thank you.